In 2001, I came to Berkeley with the intention to do a PhD in theoretical computer science. Luca Trevisan had just joined the department, and he was assigned to be my temporary advisor. He was interested in many things at the time, and among them was the then nascent area of graph property testing. Property testing was something that looked very promising because whatever question you asked, chances were that an interesting algorithm would come out of it. And in particular, many natural graph properties that people were wondering about, like bipartiteness, turned out to be testable in sublinear time with very new and interesting algorithms. One curious question was whether there were any exceptions to this at all. And this was answered at the first conference I attended, which was Fox 2001 in Las Vegas. At that conference, Luca presented a work he did with Odette Goldreich, in which they showed that there exist monotone dense graph properties that do require linear time to exist. Namely, they require looking at almost the whole graph. At that time, I knew very little about what research is. And I went around asking, and the common piece of advice that we were given is that one should talk to people. So I tried talking to Luca, but talking to Luca was not easy. Not only did he seem to know everything that was ever worth knowing, but the way that he handled questions is that he would give a one-line concise reply, and then I would sit there in silence or not knowing how to continue the conversation. I had a bit better luck talking to Kenji Obata. Kenji was a fellow graduate student of mine at UC Berkeley. And we joined Berkeley at around the same time, but he had already started working on a project in Luca by the time I started looking into these things. What they wanted to know was whether a lower bound like the one that Luca and Odette had proved can be obtained also not in the dense graph model, but in the bounded degree sparse graph model. Kenji told me that he had come up with some ingenious construction, and what he did was he constructed a graph which was far from being three-colorable, but the graph had this property that if you looked at any sublinear-sized induced subgraph of it, the subgraph would be three-colorable. Kenji's construction was very clever, and at that time I didn't understand it at all. My conclusion of talking to him was that research takes incredible knowledge, a lot of insight and ingenuity, and at the time I was not confident at all that I possessed any of those skills. A few days later I was sitting in a cafe, and I recall that the previous semester I had taken a course on the probabilistic method, and in there was a theorem of Erdős that I had learned about. What Erdős's theorem says is that there are graphs that have arbitrarily large chromatic number, but if you look at any sublinear size subgraph, it's not even it is three-colorable. And this sounded very close to what Kenji was telling me about. So what a coincidence that was to discover this connection. What did Erdős actually prove? He proved more. He showed that if I take a random sparse graph, it's going to have both properties with high probability. On the one hand, the random sparse graph is unlikely to have large independent sets. So for this reason, it's unlikely to be three-colorable. Not only is it unlikely to be three-colorable, but turns out that a random graph is about as far from being three-colorable as any graph could ever be. The second property also turns out to be satisfied with high probability by a random graph. If I take a sublinear size induced subgraph of a random graph, it is likely to have a three-coloring. The reason is that subgraph of a random graph are sparser than the host graph. So it is quite likely that within every sufficiently small subgraph, there exists at least one vertex of degree 2. And now that we know that there is a vertex of degree 2, we can find the three-coloring iteratively. We remove this vertex, color the rest of the graph, three-color the rest of the graph, and then assign the one unassigned color to this vertex, and that completes the three-coloring. I was very excited to find this, and I ran up the hill to Luca's office to tell him what I found. You have to walk quite a steep hill to get there, and when I arrived there, I was out of breath, and I told Luca, I think I have a different proof of the result that Kenji got. Luca looked at me and he says, sit down and maybe you should quit smoking. And then he listened to what I had to say. The real objective was to prove not a one-sided, but a genuine two-sided lower bound for testing colorability. And that's when Luca sprang into action. And Luca's insight was that one shouldn't look at graphs, but one should look at systems of modular linear equations that are sparse. In hindsight, we now know that this is the real interesting problem in algorithms and complexity theory. So what Luca realized immediately is that using Gerdash's idea, one can construct two distributions on linear systems, one of which is satisfiable, and the other one of which is far from satisfiable. And in addition, this will have the property that if I look at any sublinear size subsystems, the two are identically distributed. Kenji and Luca had already come up with a reduction from solving linear equations to the problem of three-colorability, which was friendly to sublinear time algorithms. And putting these two insights together, the theorem that they wanted was proved. This was an accidental project that I ended up doing with Luca and Kenji, but it was really instrumental in boosting my confidence to pursue a career in theoretical computer science. My conclusion was that all I had to do was to read something interesting in a book, and of the chance that Luca didn't know it already, I would tell him and he would handle the rest. In reality, what it taught me was the important lesson of what research is all about. What matters in research is not if the answer takes years of specialized training to get to, or if one is lucky to come across it in a serendipitous conversation with Luca and Kenji. Research is about working through the confusions in one's mind to arrive at the right questions. And in this respect, Luca's mind was as clear as any. The boundaries between what he knew, what he wanted to know, and what he wasn't interested in were very sharp. Such self-awareness can only be achieved through extreme intellectual honesty, a standard that most of us can only ever aspire to attain. Luca and I stayed in touch throughout the years, and he was there for some of the happiest moments in my life. I miss him.